Good day, everyone. I am Christy Tino, and I will be starting our presentation on a critical concept and engineering management, the fundamentals of game theory. This topic is essential for understanding strategic decision making in competitive environments. For the introduction, game theory was primarily developed in 1944 by John von Neumann, a Hungarian-American mathematician, and Oskar Morgenstern, a German-American economist. Their foundational work, a book published in 1950, titled Theory of Games and Economic Behavior, established game theory as a new field of study. They develop a mathematical framework to analyze strategic interaction and decision making, especially in economics. Game theory was started in 1944 by 2K developers, John von Neumann, who was a math expert, and Oskar Morgenstern, who was an expert in money and business, or in economics. They are the ones who created the theory. They wrote a famous book named Theory of Games and Economic Behavior. This book officially made game theory as a real subject for study. They created a math system to study how people make smart choices or strategic decision, especially in the world of business and money. Game theory is a mathematical and analytical tool used to study how people, groups, or companies make decisions when they are in competition or negotiation. What is game theory? Game theory is the study of strategic decision making in situations where the outcome of one person's choice depends on the choice of others. This means that you are not the sole decision maker. The results, the outcome, or the success you achieve do not depend on your choice alone. Instead, the final result is determined by the overall combination of the plans and decisions made by everyone involved, including your group or your opponents. Think of it as the mathematics of negotiation and competition. It's not just about playing games, it's about modeling real world interactions to find the best course of action. Game theory is also a mathematics of negotiation and competition. It's not just about playing games like chess, it's all about a real world situation where people, companies must decide what is the best strategy to get the best outcome. A game is a contest involving two or more decision makers, each of whom wants to win. A game in game theory refers to any strategic situation or contest where there are two or more individuals or entities, the decision makers or players. Each player is assumed to have their own interest and primary goal, which is typically to win or to achieve the greatest possible benefit for themselves. Game theory is the study of how optimal strategies are formulated in conflict. Therefore, game theory is the academic study focused on determining how players should formulate their optimal strategy or their best possible plan of action within that situation of conflict or competition. The goal is to find the strategy that maximizes your own success, regardless of what the other players choose. Let's proceed to key elements of a game. First is the players. These are the people, groups, or companies that are making decisions in the situation. They are the ones competing or negotiating. In engineering, they can be rival firms, project teams, or different departments. Second is strategies, the complete plan of action that a player will take, given the possible actions of the other players. This can be a simple action or a complex sequence of choices. So, this is the complete plan of what a player will do. It's not just one move, but the whole plan, including how you react to every possible action the other players might take. It can be a simple choice or a complicated series of choices. Lastly is the payoffs. This is the final result, reward, or outcome that each player gets at the end. The payoff depends on everyone's strategies combined. This result can be measured as money, bigger market share, saving time, or any other win. Advantages. First, structured analysis provides a clear, formal mathematical framework to model and analyze strategic interdependence between the rational players. Game theory gives us a clear scientific template or framework like a math table to study complicated strategic situations. It helps us organize all the players and their choices so we can analyze them properly. Predictive power identifies stable outcomes like the Nash equilibrium and optimal solution for zero-sum game, aiding in production and strategy selection. This theory can predict the stable outcomes of a game, meaning it finds the result, like the Nash equilibrium, that no player will want to change. This is useful because it helps you choose the strategy that has the best chance of succeeding. Then highlights conflict and cooperation, clearly demonstrates how individual self-interest can lead to suboptimal collective outcomes. Example, prisoner's dilemma, explaining the need for cooperation or regulation. It shows us that if everyone acts only in their own best interest or self-interest, the whole group might end up with a worse result, like in the prisoner's dilemma. This explains why we often need rules or cooperation to get the best result for everyone. Lastly is wide applicability. Game theory is a flexible tool that is useful in many areas, not just business. Experts use it in economics, studying politics like international relations, understanding biology, and creating military strategy. Disadvantages assumes perfect rationality, fails to account for real world human behavior, influenced by emotions, biases, errors, or notions of fairness. Game theory assumes everyone is perfectly logical and will always choose the option that gives them the most benefit. In the real world, people make decisions based on emotions, personal feelings, or mistakes, which the theory does not consider. Then requires complete information. Many models require players to know all the rules and critically all other players' payoffs, which is rarely true in reality. To work perfectly, many models need players to know everything: the rules, all the possible moves, and even the exact gain or loss of every other player. In reality, we almost never have all the information. Multiple equilibria. In complex games, the theory of 10 predicts many possible stable outcomes, limiting its ability to precisely predict which one will occur. For complicated games, the theory sometimes gives too many possible answers, many stable outcomes. When this happens, game theory can tell you which one will actually happen, so its ability to predict the future is limited. Lastly is high complexity. Modeling games with many players or strategies becomes quickly computationally and mathematically complex exponential growth. So, when you add more players or more possible moves, the math required to solve the game becomes extremely difficult and complicated. This makes it hard to use the theory for very large real-world problems. Let's proceed to types of games. First is cooperative versus non-cooperative. For cooperative, players can form binding agreements. Example, two engineering firms forming a joint venture to bid on a large project. So, for cooperative, this is when players are allowed to talk and make binding agreements with each other. They work together to reach a common goal. For example, is two companies agree to work together to win a big project, sharing the risk and the profit. For non-cooperative, Players cannot form binding agreements. Example, two companies competing for the same contract. So for non-cooperative, these games focus on individual decision making. Players cannot form binding commitments or communicate effectively. Each player must independently choose the best strategy for their own interest. Second is simultaneous versus sequential. For simultaneous, players make their decision at the same time without knowing the other's choice, meaning players make their moves at the exact same time. You must choose your action without knowing what the other players had chosen. And then for sequential, players make their decision in a specific order, with later players have knowledge of earlier players' actions, meaning players move in an order like taking turns. The players who moves later knows what the earlier player have already done. Next is zero sum versus non-zero sum. For zero sum, one player's gain is exactly equal to another's lose. Example, a simple bidding war where the winner takes all and the loser gets nothing. Meaning, whatever one player gains, the other player loses the exact same amount. In a simple explanation, if one firm wins 1 million, the other firm loses the chance to earn that 1 million. Then, for non-zero sum, the sum of the payoff is not zero, meaning the outcomes don't have to balance out. It is possible for both players to win or for both players to lose. For example, is a partnership where both companies benefit greatly, or a trade war where both economies suffer severe losses. Language of games. For K assumption, players are assumed to be rational. They will always choose the strategy that maximizes their personal payoff or minimizes their losses. So, in game theory works by assuming that all players are smart and logical. They will always choose the plan that gives them the most benefit or the plan that causes them the least loss. And then in focus type, two-person and zero-sum game. Games between two players where the gain for one player exactly equals the lose for the other. This is the simplest type of a game. It only has two players and it's an all or nothing contest. If one person, for example, wins 100 million, the other person loses exactly 100 million. There are no shared gains or shared losses.
So good day everyone, I am Sherwin JT also and I will be continuing the report about the fundamentals of game theory. The first one is the language of games. So the player roles, the player X or the row player seeks to maximize winnings, while the player X, the column player, seeks to minimize losses. The payoff matrix is a table showing the outcomes or the payoffs for every possible combination of strategies. So here is the figure for the game outcomes. The store X's strategy, store Y's strategy, and the outcome. And then the other figure is the game player Y's strategy and the game player X's strategy, which is the payoff matrix ni siya nga figure. So a positive number means that X wins and Y loses. A negative number means that Y wins and X loses. Pure strategy games. In some games, the strategies each player follows will always be the same regardless of the other player's strategy. This is called a pure strategy, a saddle point in a situation where both players are facing pure strategies. The strategies for saddle points games can be determined without performing any calculations. So the saddle point here is the 3. So looking at payoffs, we can see that X will always play strategy X1. The lowest or worst outcome for playing this strategy is better than the best outcome for playing this strategy is better than the best outcome for playing the other strategies, which is the X2. Thus, player X will always play strategy X1, knowing this to minimize losses. So Y will always play strategy Y1. The loss for playing strategy Y1 is 3, while the loss for playing Y2 is 5. So the loss is lesser than the other. So the next one is the minimax criterion. So minimizing one's maximum losses is identical to maximizing one's minimum gains. In game theory, this is called the minimax criterion. This criterion is one approach to selecting the strategies that will minimize losses for each player. So the minimax criterion is a decision-making rule used to minimize the maximum possible loss, risk, or cost in worst-case scenario. It is a pessimistic or conservative approach often employed in situations of uncertainty where the probabilities of different outcomes are unknown, or in game theory where there is an adversarial opponent. So in the essence, the strategy involves two steps. The first one is find the worst case scenario for each available strategy or action. Identify the worst possible outcome, the maximum cost or minimum payoff or profit that could occur. The next one is choose the best of the worst. Select the strategy whose worst case scenario is the best among all the worst case outcomes. And the next one is mixed strategy games. So where there is no saddle point, players each strategy for a certain percentage of time. This is called a mixed strategy game. And the rest of this is supplement investigates ways to determine the percentage of the time that each strategy will be played. For a 2 by 2 games, where both players have only two possible strategies, an algebraic approach can be used to solve for the percentage of the time each strategy is played. So a mixed strategy is a concept in game theory where a player chooses a probability distribution over their set of pure strategies. Instead of selecting one specific action with certainty, the player randomizes their choice of action based on these probabilities. So, why use a mixed strategy? So, players use mixed strategies primarily in games that lack a pure strategy or Nash equilibrium. One of the main reasons are unpredictability. By randomizing a player prevents their opponents from exploiting a predictable pattern. This is crucial in zero-sum games. An example for this is rock, paper, scissors. So this game perfectly illustrates the necessity of a mixed game strategy. If you always play rock, a pure strategy, your opponent will eventually notice and always play paper, beating you every time. So the only Nash equilibrium is rock, paper, scissors is the mixed strategy where each player chooses rock, paper, and scissors with equal probability. So the probability is equal to 1 over 3. Any deviation from this 1 over 3 probability allows the opponent to change their strategy and achieve a higher expected payoff, meaning the one-third distribution is the only stable outcome. Next is dominance. So the principle of dominance can be used to reduce the size of games by eliminating strategies that would never be played. A strategy for a player can be eliminated if the player can always do as well or better playing another strategy. In other words, a strategy can be eliminated if all its game's outcomes are the same or worse than the corresponding game outcomes of another strategy. So using the principle of dominance, we reduce the size of the following game. So in this game, x3 will never be played because x can always do better by playing x1 or x2. The new game is this one. So dominance is a foundational concept in game theory that describes a situation where one strategy is objectively superior or inferior to another strategy, regardless of what the other player choose. So the principle of dominance is used to simplify a game by eliminating choices that a rational player would never make. So this process is called iterated elimination of dominated strategies, or IEDS. So the prisoner's dilemma. So the prisoner's dilemma is a game in strategic form between two players. Each player has two strategies called cooperate and defect, which are labeled C and D for player 1 and C and D for player 2 respectively. So classic example is the scenario is two prisoners caught for a crime are interrogated separately. They have two choices, which is to confess or to remain silent. The payoff matrix is it display a simple 2 by 2 matrix showing the outcome for both players for each combination of choices. If both remain silent, so the light sentence is 1 year each. So if one confesses and the other stays silent, the confessor goes free, and the silent one gets a long sentence which is 10 years. If both confess, both get a moderate sentence which is 5 years. The dilemma here is the best individual choice confessing leads to a worse collective outcome for both players. This illustrates how acting in self-interest can prevent cooperation and lead to a suboptimal result. So the prisoner's dilemma is the most famous example in game theory. It is a non-zero sum game that beautifully illustrates a paradox. When two rational individuals pursue their own self-interest, the outcome is worse for both of them than if they had cooperated. So it highlights the conflict between individual rationality, doing what's best for oneself, and collective rationality, doing what's best for the group. And lastly is the Nash equilibrium. So Nash equilibrium is a stable state in a game where no player can improve their outcome by unilaterally changing their strategy. Assuming the other players keep their strategies unchanged, it's a point of stability. It's where each player is making the best response to the other player's best response. Think of a traffic jam where no car can move forward by itself. Everyone is at a standstill, and no single driver can change that situation on their own. So the traffic jam is a stable state, a type of Nash equilibrium. The Nash equilibrium is the most important concept in non-cooperative game theory. It is a set of strategies, one for each player, where no player can unilaterally change their strategy and achieve a strictly better outcome or payoff, assuming the other player keep their strategy unchanged. So in simple terms, a Nash equilibrium is the stable state in a game. Once the player are at this set of strategies, no one has an incentive to be the first to deviate. The key principle of Nash equilibrium is the best response to others, and Nash equilibrium occurs when every player's strategy is the best response to the strategy chosen by the other player. So no regret if a player is playing their Nash equilibrium strategy and they knew what the other players were going to do, so they still wouldn't regret their choice. So rationality and knowledge. The concept assumes that all players are rational. They seek to maximize their payoff, and they know the payoff and strategies available to all other players. And so that is it for our report, and thank you for listening.